A.C. Patra, General Manager CNS, to please step onto the dais. Welcome, sir. Mr. Hiromi Miyazaki, Chief Researcher, Electronic Navigation Research Institute, Japan. Dr. Bala K. Bhardwaj is the Managing Director of Boeing Research and Technology, Bangalore, and Leader of India. May we have you on the dais? Doctor, welcome. Dr. P. Lakshminarayan, sir, Principal Scientist, Research and Training Unit for Navigation Electronics, NERD to Osmania University. Welcome. We now have our moderator and three speakers seated on the dais. To begin with, we would like to have a felicitation for them. I would like to call upon Mr. Nehru to please step forward. I request you to kindly hand over a floral welcome, a felicitation, to our moderator, Shri S.K. Patra. General Manager CNS. Welcome. I'd like to call upon Mr. Banu Shekhar, AAI Chennai. Chennai Pasanga, please. To hand over a floral welcome to Mr. Hiromi Miyazaki, Chief Researcher, Electronic Navigation Research Institute, Japan. Thank you. Mr. Kumarasamy from AAI Chennai. To hand over a floral welcome to Dr. Bala K. Bhardwaj, Managing Director of Boeing India, Bangalore. Welcome. And Mrs. Sarvana Kumar, to hand over a floral welcome. AAI Chennai, Mrs. Sarvana Kumar, welcome. To hand over a floral welcome to Dr. P. Lakshminarayan, Principal Scientist, Research and Training Unit for Navigation Electronics, Osmania University. Thank you, gentlemen. We will have the first technical session. We'll have speaker 1 speaking, speaker 2, speaker 3. We'll have our moderator doing his moderation. And then we would have the floor open for the Q&A. So all those who have any doubts can jot it down in the letter pad. So we will have a Q&A session after the first technical session 1. The first speaker for the technical session 1 is Mr. Hiromi Miyazaki, Chief Researcher, Electronic Navigation Research Institute, Japan. Mr. Miyazaki holds a postgraduate degree in electronics engineering from Shinzu University, Japan. He joined ENRI in the year 1993 in the Surveillance Research Group. His main interest of research is aeronautical surveillance technologies. His current research focus is in developing hybrid surveillance technologies, establishing a data integration to link conventional systems, secondary surveillance radar, to the new systems like wide area multilateration and ADS-B to cover the transition period to the new systems. Mr. Miyazaki was a member of the team which had successfully completed a radio over fiber technology to introduce better interference immunity to MLAT systems in a multi-part environment. Currently, the result of this research is under implementation in Sendai Airport under the code name OCTPass, OCTPASS, Optically Connected Passive Surveillance System. Today, Mr. Miyazaki will take us through the development of wide area multilateration technologies in ENRI. Over to you, Mr. Miyazaki.
And at first, hello everyone. At first, I'd like to tell you thank you very much for inviting us for this nice event, DISA 2015. Today, I prepared 2 presentations. One is introduction to ENRI, and another one is one of our research activity, wide area multilateration. So, at first, I provide you introduction of ENRI. interrupted. So at first, what is ENRI? ENRI means Electronic Navigation Research Institute. ENRI was established in 1967 as a national laboratory. As a tiny information, I was also born in 1967, so I'm same age with ENRI. I'm 48 years old. This is information. So a major research fund comes from Ministry of Land, Infrastructure, Transport, and Tourism. The budget is about 1.7 billion. This is about 3 billion Indian rupee. The personnel, there are 66 personnel. The major research area is, at first, air traffic management, and of course, navigation system and surveillance system and communication system. The major role, of course, firstly, research and development and test for future aviation systems. And next major role is contribution to establishing technical standards. For example, ICAO, SERPs, RTCA, and EuroCAE, European standard. And we have many collaborations in the world. Excuse me. For example, University Nice Sophia Antipolis. This is French laboratory. And NASA, it's very famous, United States National Laboratory. And Korean Aerospace Research Institute. And the major research and development activities ND, for example, for airport operation, we analyze airport traffic, for example, bottleneck mitigation. And ZBus prototype, now we have developed ZBus prototype. For this item, in this afternoon session, my colleague, Dr. Atsushi Kezuka, provides you details. And another topic is aeronautical mobile airport communication system. We call AeroMax. AeroMax is a new generation high-speed air and ground data link based on WiMAX. So we have conducted evaluation tests in Sendai Airport. Another topic is Octopus. Octopus means optically connected passive surveillance system. This is actually multilateral system, advanced multilateral system. Key point of Octopus is its very high accuracy with very compact system configuration. And one more topic is millimeter wave radar network for debris warning. Henry developed an optically fiber-based 94 gigahertz radar network to extend coverage of debris detection. For seamless sky in the future, we believe harmonization is very important. Of course, harmonization among different aviation systems and harmonization between different standards, ICAO, EuroCAE, RTCA. So, Henry will work hard to continue to realizing seamless sky from technical point of view. So, this is introduction to Henry. So, I'd like to succeed next presentation. excuse me. The next presentation title is, excuse me for interruption. Title is Development of Wide Area Multilateration. We call WAM. WAM technology in Henry. As introduction, increasing aviation demand requires capacity and efficiency for air traffic control ATC. So a new advanced air traffic management will be introduced in many regions. So it's also for this new management necessary to implement high-performance surveillance system, such as WAM and ADSB. ADSB is new style surveillance system based on GNSS technology. So, therefore, Henry has developed WAM and ADSB technologies. What is the motivation for this work? A main objective of WAM and ADSB development is to expand coverage for en route surveillance with less receiver configuration, co-location. This is required to improve performance, especially outside the receiver co-location. So, one of the solutions is to apply measured range between receiver and aircraft to WAM localization. We call this technique ranging. This presentation is divided mainly 3 sections. At first, I describe purposes of this development. And next, I explain about overview of our experimental WAM system. Lastly, I indicate test results of performance evaluation for this WAM system. So let's start first section, purposes of the development. As demands for aircraft operation, user, this means passenger wants to reduce travel time and travel cost. And aircraft operator, this means air carrier, seeks efficient flight for time and cost. And air traffic controller, this means service provider, wants efficient flight with safety and taking environmental care. So for this situation, we need any new style air traffic management. The most famous advanced air traffic management is 4D trajectory operations. 4D trajectory operations consist of some elements such as dynamic airspace allocation, traffic sequencing, and complexity management. For the aeronautical surveillance system, so this conflict detection and resolution is the most important. For the 4D trajectory operations, ATC surveillance system has to be high accuracy and high update rate. This is because it's very important to get aircraft current and future positions exactly. But unfortunately, conventional SSR update rate is about 10 seconds for en route surveillance, depending on antenna location speed. So actually, this is not sufficient. So why high update rate and accuracy are needed? It's important to predict short-term future positions. In this situation, air traffic controller and air traffic system predict future position here. Future position here. But actual aircraft position is here. As you can see, low update rate and low accuracy surveillance system result in delayed conflict detection and resolution. On the other hand, high update rate and high accuracy surveillance system could avoid this dangerous situation. So we need any high update rate and high accuracy surveillance system for the new traffic management. As I told you, ADSB, Automatic Dependent Surveillance Broadcast, is considered as the next surveillance system. ADSB is able to achieve high update rate and high accuracy. But however, new avionics are required to aircraft side, and also security protection methods. Any security protection methods are needed. So we need any other surveillance system to complement or transition period. So WAM and ADSB is the best combination. What is WAM? WAM is its alternative high update rate and high accuracy system. WAM detects signals transmitted from aircraft SSR transponder in a number of receiver stations and locates the aircraft position using TDOA technique. TDOA means time difference of arrival. So WAM is one of hyperbolic navigations. Position accuracy of WAM is better than SSR, and update rate is 1 or 2 seconds according to transponder signal transmission. Unfortunately, there is some drawbacks of WAM. Basically, we need a number of receiver stations for the WAM. This picture depicts a map of Japan. As you can see, Japan is surrounded by sea. In this situation, we could not install receiver station on the sea, of course. And in addition, there is many mountain area in Japan. So in this situation, it's difficult for us to get power source and communication line. So this is very big issue for logistical issue, site establishment and communication line. Another drawback is that position error increases rapidly, especially outside the receiver collocation. So any technique is desired to improve performance, especially outside the receiver collocation. So key point of WAM development is balance between cost and performance. So for the drawbacks, one solution is ranging, as I said before. If the WAM system transmits SSR interrogation to the aircraft, the WAM system can get reply from the aircraft. And the system can calculate the range from the time between interrogation transmission and reply receiving. So in the ranging technique, for the normal WAM, hyperbolic lines by TDOA calculation intersect in nearly parallel, especially outside the receiver configuration for this situation. On the other hand, circle line by the time from interrogation and to reply intersect at a right angle with TDOA hyperbolic lines. So ranging could improve accuracy and update rate, especially outside the receiver collocation. So let's move to the next section, overview of the WAM system. This figure represents a block diagram of receiver station. Some advanced techniques are adapted for the receiver station. For example, the most important block, timing. So the sampling frequency of time tagging is about 500 megahertz. This means time resolution is 2 nanoseconds. And common view GPS technique is used for the time synchronization among receiver stations. In our experimental system, the system consists of 1 target processor and 8 receiver stations. 1 receiver station equips a transmitter unit. So if a WAM system equips interrogation capability to aircraft, we call this system active WAM. This means for interrogation. On the other hand, if the WAM system does not have interrogation capability, we call passive WAM. So, and this WAM system is active WAM. This figure represents collocation of receiver stations with H-dop. H-dop means horizontal dilution of precision, which is famous for GPS accuracy. The experimental system has been installed Tokyo International Area. So based on this H-dop distribution, we set the WAM system coverage to about 60 nautical miles. This picture shows an antenna installation situation in ND, our research institute. WAM antennas are installed in high place as much as possible to avoid signal interference. So from now, I provide you final section, test result of performance evaluation for the WAM system. This picture shows our experimental aircraft, King Air 350. The evaluation test was conducted using this experimental aircraft. This figure depicts tracks on the performance evaluation. Blue line shows wide area multilateration, and gray line shows ADS-B. As you can see, over 40 nautical miles is outside the receiver collocation. So it is expected the performance degradation occur over the 40 nautical miles due to H-dop increase. This figure represents a comparison of position error distribution to confirm achieving high performance for the evaluation system. The evaluation test was conducted by comparing passive WAM and active WAM. Passive WAM realized offline data analysis. So as you can see, it is, as we expected, For the passive one, blue dot, position error increased rapidly over 40 nautical miles based on the bad H-dot distribution. This table shows a comparison of position accuracy between passive worm and active worm. As you can see, active worm conducting interrogation to aircraft can keep good performance outside the receiver collocation. This means 40 nautical mile and 60 nautical mile. Whereas passive worm facing performance degradation for this coverage. Performance, accuracy is about 144 meters. So it is considered Henry's worm experimental system is able to achieve high performance. So as conclusion, I provide you a movie by collected data for the tracks between among WAM, ADSB, and SSR. The red line means WAM tracks, and yellow triangle means SSR, and white line means ADSB. As you can see, WAM tracks is almost same with ADSB track. ADSB is calculated by GNSS, so it's almost true position. On the other hand, SSR update rate is about 10 seconds, but WAM update rate is 1 second. So WAM can achieve high update rate, high accuracy compared with conventional SSR. So here is Tokyo International Airport. So my presentations, that's all. Thank you very much for your attention, and thanks again for inviting us. So any question?
Myself, Santosh from Bangalore.
Yep.
My doubts are this receiver time synchronization, that is you are doing by GPS only. So how far it will be accurate?
Oh, I see. Did my English.
Oh,
thank you very much for your Japanese. It's easy for understanding.
はい、質問はですね、
はい、
GPS の、
はい、
その赤道ですか、アキュレーシーが、
はい、
あんまりちゃんとじゃないから、
はい、
ここでどのぐらい、そのアキュレーシーが出てくるか。
なるほど。はい、oh, thank you for the question. So actually, in Japan, ADSB position accuracy is about from 30 meter to 100 meter, depending on transmitting timing from transponder for ADSB avionics. So, but on the other hand, the WAM system accuracy, the true position, we use true position as kinematic GPS. So this means offline processing. So WAM system is very true value, I think. But I think so. But ADS ICAO is considering ADSB performance. It's sufficient. ADSB performance is about. Excuse me, it's difficult. Maybe 100 meter is okay, I think. But most key point is the ADSB performance depends on avionics side. So this means most important thing is transmit timing with GPS calculation time. So for my reply is sufficient for you?
Warm welcome in India, first of all. I would like to ask when you said about the cost and the performance, the drawback. So the cost and the performance in terms of the drawback, no, sir?
Okay. Good question. If we are in one system, if we take high performance, we have to install much receiver stations. This means the cost very increasing, installation cost, maintenance cost. But service provider or Japan Civil Aviation Bureau hate this cost increasing. So on the other hand, if we decrease a number of receiver stations, of course, one performance decreasing. So the key point again, if we install one receiver unit, many receiver units, stations, the one system, performance of one system could improve. So this is my response.
Thank you, sir.
Yeah.
Sir, the solution you said ranging, na?
Yeah.
In terms of performance. I want to ask this, ki how you will get circular lines instead of hyperbolic lines. We have to make technical difference in the designing part or something else in order to get circular lines instead of hyperbolic lines.
Yeah. So especially outside the receiver configuration. So passive one, if we use passive one, we face performance degradation rapidly. But if we use active one, circle line, improve performance, especially outside the collocation. The one transmitting equipment is equal with 3 or 4 receiver stations. So this active one capability is very attractive for cost benefit. So is it okay?
No, sir. I want to ask, is there will be any designing difference if we want to have circular lines? You have said, na, they will be right angle intersection if we will get circular lines. And we will get parallel intersection if we will use hyperbolic lines. So we are preferring circular lines instead of hyperbolic lines. How you will rectify this thing? I am asking this.
私説明しますが、ですね、今ハイパーボリックのために何か角度テクノロジーですか、サークラーテクノロジーを何かこのやり方が違うんですかという質問ですね。
そういうことですか。So hyperbolic lines is decided by the receiver configuration. So this topic is very detailed. So if you are okay, after this session, we discuss about this topic. Is it okay for you?
Okay, sir. Thank you. Thank you.
Excuse me.
Could you please repeat what is the difference between passive worm and active worm?
Yeah.
Can you repeat, please?
パッシブワームとアクティブワームの説明をもう一度。
Okay. Basically, worm is passive worm. Passive means the worm system does not have interrogation capability to aircraft, only receiver. So normal worm is passive worm. So this means does not transmit interrogation. On the other hand, active worm means the system has interrogation capability for transmitting for interrogation. So by interrogating to the aircraft, the system can improve accuracy or update rate. So the interrogation capability is very effective to improve performance. So there is a difference.
But for calculating the time difference, you will need some interrogation.
Yes,
in
interrogation.
passive.
Yes.
So what is the interrogation? Is it ADSB interrogation you are using or ADSB transmissions you are using?
So this interrogation is for basically secondary surveillance radar. So, but ADSB does not need interrogation capability.
True. But for calculating the time difference, TOD, time difference of arrival, you will need some sort of interrogation. Or is it just quitting, you mean to say, in passive FIM? Just quitters are there. Maybe.
私、この辺説明しますが、パッシブの時はですね、何もイントロゲーションがないということですね。でも彼の質問は、少なくても何かイントロゲーションが必要ということです。パッシブの時はどうやってそのイントロゲーションをやるか。
Okay, I realize your question exactly. The aircraft transmit a signal. This signal means, as you said, ADSB. And one more important signal is from ACAS, Air Collision Avoidance System. ACAS system transmit signal. This is same with SSR. One times per second. So passive one usually calculate aircraft position using this skitter for ACAS system. Thank you.
Thank you very much.
Sir, excuse me. Please go ahead, sir. Geographical location of the receivers?
Yeah. Oh, thank you for your information. A good question. For multilateration, important position is horizontal position because height information is, air traffic controller use height information for barometric altitude information. So in the one system, important dop is H dop, not G dop. So use usually H dop.
So next, Mr. L.N. Prasad.
Yeah.
Good morning.
Good morning.
Welcome to our DISA 2015.
Thank you.
I come from the Flight Inspection Unit of Airport Authority of India.
Yeah.
So definitely I would like to know, first of all, my question consists of two parts. One, we being in equatorial region, what additional precautions we need so far as the HDOP accuracy is concerned? Because for our ionosphere model will be different to what exists for you in Japan. So what additional features we will be needing to do for implementation of your system here in our country? That is number one. The second part of my question is, what flight evaluation techniques we need to adopt so that these procedures can be standardized?
Okay.
質問、繰り返します。
Thank you.
ですね、彼の質問は2つのパーツになって、最初は、例えば日本のそのジオグラフィーですかね、山とか、海が囲まっているんですけれども、インドの方はかなり違ってる、天理的ですかね、アイオノスフィアの。その違いは、このシステムどうやってそれ、使うか。あと2番目はですね、このフライトアキュレーシーのために、何かどういうような装置とか使うか。質問。
Thank you. Surrounded by sea, and there are many lot of mountain area. So in this situation, the radio wave are restricted by line of sight or interference. On the other hand, there is flat area. One system, it's easy for us to construct one system because of there is no obstruction. So, is it okay for my reply?
With relation to the ionospheric model I was talking, so basically there is a changed requirement as far as implementation in India goes. Like it is different for implementation of GBAS in probably Japan and India, there is a sizable difference. So with relation to that, implementation of this technology, that's what I wanted to know.
Okay.
GBAS の実施に関しては、日本とインドのそのアイノスフィアの面から見ればかなりの違いがあると。でも WAM のところでどういう違いがあるか、装置の設備ですかね、それに関して。
Okay. Thank you for your question. This opinion, basically, there is no difference for the system, receiver station, between Japanese environment and Indian environment. The difference is, I think, the number of receiver station, the needed receiver station, I think. And for your second question, the experimental aircraft, it's very simple system. The system, experimental aircraft has to be equipped transponder, appropriate transponder. This means new style, basically SSR Model S transponder, and in addition, if possible, ADS-B capability. And if we calculate position accuracy, the experimental aircraft has to be equipped high precision GPS system. I recommend you.
So next, Mr. Perumal, General Manager from Chennai.
Criteria. That is very vital one. What type of communication you are doing? This WAM implementation is very difficult. We can make it, but the WAM implementation, that main thing is the communication. How to make the lines. Then sighting also. Sighting also matters. So how you are implementing in Japan?
質問説明します。自身のところはどうやってカバーしているか、それをに関しての質問。
Thank you. High-speed communication, high bandwidth communication line. So in Japan, in the world, the WAM system need to install optical fiber line between target processor and receiver stations. So in the rural area, we have to install at first communication optical line and next install one line, I think. Is it okay?
Is it okay? No, how that ultimately OFC only you are going to use optical fiber communication. So
最後にオプティカルシステムですかね、オプティカル通信を使うから、多分前と同じかなという考えですね。何かそのオプティカルファイバーじゃなくて違うやり方があるかなというように思ってて。
I see. Some Asian country I heard they use radio VHF radio communication line. I heard this is Kuala Lumpur or Malaysia, but there is a little concern about time delay for communication. But basically, it's possible for the radio communication line, I think.
Okay, thank you.
Mr. Muruganandam,
Yes, thank you.
that you are using multilateration techniques
Yes.
combined with SSR
Yeah.
and ADSB reports
Yes.
in order to predict the position of an aircraft.
Yeah.
Probably for introducing a trajectory-based operations.
Yes.
Have you evolved any trial-based TBO procedure for evaluating the performance of your system?
Okay. Good question, but so excuse me. I could not provide you a good example, a good reply. But the system surveillance system performance is decided by the mainly traffic separation. So excuse me, I could. I'm sorry.
Then I wanted to know when this project is expected to finish.
Okay. Thank you. Actually, next year is final. This is actually experimental system, but Japan's Civil Aviation Bureau, JCAB, is going to install one system this area, operational system, 3 years later. So for your question, this research activity will complete next year.
And thank you very much for your all interactions. And the ADSB and the wide area multilateration, these are upcoming technologies in which our India is having a front runner for that. And we have enough time to interact with the delegate or designate. And you can, after this session, you can have an interaction regarding these technologies. Thank you very much for your interactions.
Thank you very much.